So let's start our next section, 12.1, which is about vector valued functions. So let's start with the definition of a space curve. A space curve, C, is the set of all ordered triples f of t, g of t, and h of t together with their defining parametric equations. So the parametric equations would be x equals f of t, y equals g of t, and z equals h of t. So we kind of saw something similar back when we talked about lines, but now we're talking about any kind of curve C in space. And so another way we can think about a space curve is with something called a vector valued function. So let's talk about what a vector valued function is. A function of the form it's either going to be f of t I plus g of t j, that's if it's a two-dimensional curve, or if it's three-dimensional, you'll have an I, a j, and a k component. I, g of t j, and of h of t k is a vector valued function. So you input in a value for t, and this function outputs a vector. And so we call these functions f of t, g of t, and h of t. These are called component functions. And these are just regular functions here, f of t, g of t, and h of t. The input is t, and it outputs a scalar, not a vector. And so the idea is here we can use vector valued functions to represent a curve. And so the idea is when you input a value of t into your function, it outputs a vector. So you would draw the vector. For example, if I input in, let's say t naught, it outputs this vector right here, r of t0. And then we're going to put the terminal point of that vector would be a point on the curve. And so maybe if I plug in another value of t, r t1, it outputs this vector right here. And again, you collect up all the terminal points when you plug in values of t, and that's going to draw out a curve in space. And these curves will have orientations to them, they'll have directions. So let's look at our first example. Let's sketch the plane curve represented by the vector valued function r of t, which will be 2 cosine ti minus 3 sine tj, and t is going to go between 0 and 2 pi. So we can start by plugging in values for t, so let's start by plugging in 0. If you plug in 0, you'll get the vector 2i. Okay, so I get the vector 2i. The vector 2i, so the point on the curve would be the terminal point of that right there. And then plug in pi over 2, you would get negative 3j, because cosine of pi over 2 is 0. So then negative 3j, it's going to point downwards. Here would be this vector. Its terminal point would be down here. Okay, and then keep doing this. So if I plug in pi, you'll get negative 2i, which will give me this point over here. If you plug in 3 pi over 2, you'll get 3j. And if you plug in 2 pi for t, you'll get 2i, which was the vector we started with. So if you start to look at this here, what am I going to get? Well, it looks like I start here and go around and around and around. And again, I'm going this way. I'm guessing that I get the equation of an ellipse. So let's see if we can verify this. Remember that we have the equation cosine squared plus sine squared equals 1. And here, go back to our equations, I look back up here, x is 2 cosine t, and y is negative 3 sine t. So if you solve for cosine, it's x over 2. And sine would be y over negative 3 squared. So if I look here, I'm getting x squared over 4 plus y squared over 9 equals 1. Sure enough, this is what we drew. It was the equation of an ellipse. So that's how I knew to fill in the picture that I had my graph.